Welcome to Science and Technology. This video is about quantum computing related news. This year marks the 50th anniversary of the Intel 4004, the world's first microprocessor and an engineering achievement that continues to evolve at a blistering pace. Riding the success of Moore's law and Dennard scaling, the computers of today draft the breakthroughs of yesterday's processors. In fact, the mobile phone or tablet you are using now has more computing capabilities than the supercomputers at the turn of the century. Fuse that processing power with the rise of machine learning and other algorithmic breakthroughs. And we are about to enter what the 2017 Turing Award winners call a new golden age of computer architecture. Arriving at this point, though, was no easy feat. Over the past few decades, the most brilliant minds in physics, computer architecture, and software design needed to band together to harness and control the classical properties of electrons for computations. Together, they built an entire ecosystem around billions of digital zeros and ones, spanning the entire stack from algorithms to compilers to microprocessor to digital gates. What we might take for granted when booting up our high-end PCs or continuously checking our phone is the culmination of decades of research, implementation and iteration, and will most likely continue into the foreseeable future. The quantum computers are beginning to emerge in many industry and research labs like IBM, Intel, Microsoft, Google, to name a few. Governments are pouring funding into quantum computing research across many countries. The number of quantum bits in these machines seem to increase every time a new prototype is announced. In the time scale of events, we are probably still in the vacuum tube era equivalent for quantum computers. System researchers call this the noisy intermediate scale quantum era, where the quantum processors are beginning to show promise for computational superiority for certain problems, but operate in a very noisy regime that is very prone to errors. In order to reach the wide scale adoption that classical computers enjoy, a lot more innovations and techniques need to be developed and implemented across the stack, similar to the classical computing evolution. At the same time, quantum computers will most likely not replace classic machines, but instead work alongside classical computers to accelerate certain applications. This is analogous to how GPU today are commonly used to accelerate graphics and pixel manipulations. To that end, quantum computing hardware is commonly referred to as QPU or quantum processing units, and will be controlled by a host processor such as CPU. In fact, a quantum algorithm typically involves classic pre or post processing and will need to be architectured in such a way to operate as a coprocessor with classical systems. Just as scientists and practitioners came together to lead us into our current information age, they must do so again for quantum computers. This time, however, rather than harnessing and taming the classical properties of electrons, the challenge is to control the quantum properties of our universe and leverage that for computing. Challenges for the future. Quantum computing truly is a cross-cutting domain which requires innovation across many dimensions. Looking back at the early days of classic computing, It took many iterations and explorations of the hardware technology until industry settled on the CMOS transistor as a de facto building block in integrated circuits. Similarly, designing a qubit and quantum system is an active area of research. Another big challenge of the post NISQ era is noise mitigation. Quantum decoherence really limits the high ceiling of quantum computing. Understanding how to build a reliable system in hardware and software is reminiscent of the 1960s and 1970s, when classical computing resources were scarce and unreliable. Doing so at the quantum level is a whole new challenge.
Thank you.